All right, so today we are continuing on, and we will look at chapters 9 and 10 in the textbook, chapters 9 and 10. So on Monday we looked at chapter 8, and we'll look at chapters 9 and 10, and then next week we'll look at chapters 11 and 12. That will be week 5, and then week 6 you'll take your final exam. So the week 6 Monday is a holiday. So next week during week 5, I'm actually going to have 3 lectures. Monday will be chapter 11, Wednesday will be chapter 12, and then Friday I will hold a review session. There's a bit of an oddity in the calendar, and I'll talk about this again next week, in that if we didn't have the Labor Day holiday, you would take quiz 5, we would have the review session, and then you take the final exam. But there's going to be kind of this weird thing where I'll have the review session, then you'll take quiz 5, and then there's nothing, and then you take the final exam. So it's a little bit strange, but that's just what happens with the calendar when we have a holiday. So I think you guys will be fine, but I just want to give you a heads up. Okay, so week 4, Wednesday, that's today. We'll look at chapters 9 and 10, and that's going to be hypothesis testing and basically statistical inference for categorical variables. Technically, we also have a confidence interval. So first we'll look at confidence intervals for a proportion, and the idea here is we're now looking at categorical variables. So we're not measuring, the height or the weight or something. Those would be numeric variables. We're not asking about the mean. We're asking about a categorical variable. So, pretty much any kind of trait that, we don't measure with a number can be kind of treated as a categorical variable. Even numeric ones we can turn into categorical variables. And when we're looking at a confidence interval, we're basically looking at one trait, and based on that trait, we have what we would call a dichotomous categorical variable. And dichotomous in this case means there's only 2 categories, and usually those 2 categories are yes and no. All right. And so an example could be, what proportion of the population, what proportion of people are diabetic? And we might, to kind of define what does it mean for someone to have diabetes, we could say, we measure their A1C level. That's kind of like this blood sugar measurement type of thing. We're going to say, is A1C over 6.5? And if it's over 6.5, you'll be classified as diabetic. And if it's under 6.5, you won't be you're not classified as diabetic. And so we can just say either people have diabetes or they don't. Okay, and that would be a dichotomous categorical variable, right? We could ask what proportion of students voted in the last election or something, and there's an election coming up in California, and it could just be, what proportion of students, voted, and either they did or they did not. It's kind of a yes or no dichotomous thing. Or, what proportion of Californians drive a hybrid or electric vehicle? So, is your vehicle just standard powered by gasoline, or does it also use, hybrid batteries, or is it pure electric or something like that? And it's just going to be a yes or no. I drive either a hybrid or electric vehicle, or no, I don't drive either of those types of things. And just like, all of the other statistical inference that we're doing, is that we want to make conclusions about the general population, but the population is this big entity that we can't observe directly, right? And so what we do is we look at a sample, and based on the sample, we make conclusions about the population. So the parameter of interest, okay, is the proportion in the population, some value P, right? So in the population, if we were able to survey all Californians, we could see, okay, out of all Californians, how many drive a hybrid or electric vehicle? or something like that, that would be some number P or some proportion P there. And we want to make conclusions about that based on some samples. So we look at, maybe a sample of 200 people. Inside our sample, we ask, do you drive a hybrid or electric vehicle? And then we draw conclusions from there, okay? So, and just like all of the other confidence intervals, we're going to create an interval of values that are maybe plausible values for the population proportion P. Okay, so based on our can you guys hear me? Okay, I'm getting network connection problem messages. So I hope this happened a couple weeks ago. The internet went out when I was doing a different class, and it was inconvenient. So okay, I'm able to see you guys. I hope this is okay. And so we're going to make a range of values, an interval of values for plausible, a range of plausible values for the population proportion piece. Okay, so one thing that our textbook does, and we'll just kind of follow what the textbook does, is we are going to use what's known as the Wilson adjusted proportion. Okay, so normally, we look at a sample, we're going to count how many observations total we have in the sample, and then we're going to count how many observations belong in the yes category, right? So the number of yeses will be Y, the total sample size is N. And so your sample proportion, your observed proportion, is just Y divided by N, right? If you have a sample of 50 people and 30 of them say yes, your sample proportion is 30 divided by 50, it would be 0.6 or 60%, okay? And that's known as P hat, okay? Our textbook uses the Wilson adjusted proportion, which it calls P tilde or P squiggle, and it adds 2 to the numerator and 4 to the denominator. So if we had a sample of 50 people and 30 people say yes, what we're going to end up doing is we're going to have 30 plus 2, 32 in the numerator, divided by 50 plus 4, divided by 54 in the denominator. And our value is going to be slightly different. Okay, it's going to be 32 over 54, which is, so instead of 60%, we get something just a little bit lower than that, 59.25%, 59.26%. Okay, so just a little bit under 60%. Why would we do such a thing? Using the adjusted sample proportion ensures that we don't run into issues where we get a proportion of 0, a sample proportion of 0 or 1, which leads into problems. So for example, let's say, you wanted to find, what proportion of people, I don't know, some rare condition, right? So you say, what proportion of people have, some fairly rare genetic condition, and you might survey 200 people, and it's possible if it's a very rare thing, you get 0 people out of 200. Okay, 0 people out of 200 would lead to a sample proportion of 0. Okay, and if you have a sample proportion of 0, then all of the calculations are going to end up getting a standard error of 0 and things like that. And that just means then you won't be able to create a confidence interval. But that also doesn't mean, just because you surveyed 200 people doesn't mean that this thing doesn't exist at all, right? Like, you might know that such a thing exists. And so instead of getting 0 out of 200, you would end up getting 2. You would add 2 to the numerator, divided by 200 plus 4, and you would get something just around 1%, okay? 1 over 102, something just under 1%, okay? And basically, it avoids issues where you get either a proportion of 0, or, if you have something else, you might have another question where almost everybody answers yes, and you might get 100 out of 100, right? You survey 100 people and all 100 people say yes, okay? Using this adjusted sample proportion, instead of getting a p hat of 1, the adjusted proportion would have 102 divided by 104. And you get something that's, a little bit different from 100%. You get 98%. It basically just ensures that you don't get a sample proportion of 0 or 100%. Okay, and that's the Wilson adjusted proportion. I would say this is, there aren't very many textbooks that bring up the Wilson adjusted proportion. I would say our textbook is fairly unique in that case. Most textbooks I've seen use p hat, where you just do y divided by n. But again, using p hat with y over n, you could run into issues where you get 0 or 1 as a proportion. Okay. All right. So anyway, once you have this adjusted proportion, the formula for a confidence interval, if you want to make a 95% confidence interval, you put your proportion in the middle, p tilde, the Wilson adjusted proportion in the middle, and you go plus or minus basically 2 standard errors. Okay, 1.96 standard errors. The standard error is given by this formula, the square root of p tilde times 1 minus p tilde divided by n plus 4. And that's pretty much it. Okay. If you wanted to make a confidence interval for other levels of confidence, say 90% or 99% confidence, you could do that, but it gets a little bit more involved. It's not just a matter of changing 1.96 to something else, but you actually have to change the way you calculate p tilde, and just to kind of avoid getting into something that's, in my opinion, a little bit more work than it's worth. As far as this class goes, we're just going to look at 95% confidence intervals for a proportion. But again, it does exist, and if you're interested, you can look it up. There's a section in the textbook that covers it. Okay, but as far as our test classes and quizzes, I'll only give you a 95% confidence interval, at least for a proportion. Okay. For means and stuff, sure, we can have other confidence levels, but for proportion, just 95%. Okay, so let's go ahead and do an example. I completely made this up, these numbers, and I want to kind of rephrase my thing because I think this number is way too high, right? So let's say you want to just know what proportion of people have Netflix, okay? And having Netflix is a very different question from do you pay for Netflix, right? Because a lot of people kind of just share accounts, and so the proportion of people who actually pay for Netflix probably much lower. Proportion of people who have Netflix or have access to Netflix probably much higher. So I don't know. I just made up some numbers here. So we're going to say we surveyed a sample of 100 randomly selected people, and in that sample, 30 people. I wrote pay for Netflix, but I think that's totally wrong. We'll just say 30 people have Netflix. Okay, and we're going to just say, what can we say about the proportion in the population that subscribe to Netflix or have Netflix? And we'll go ahead and make a 95% confidence interval for P using the Wilson adjusted proportion. Okay, so we'll go ahead and do this just real quick. And then we'll go over. All right, so first we're going to start off by calculating. Something's wrong with me. Okay, P tilde, we got y plus 2 over n plus 4. And right now our y is, we have 30 and we have n equal to 100. So I'm going to have 32 divided by 104. And 32 divided by 104. 0.3077. Okay. All right, and so we'll have P tilde plus or minus 1.96. So it's really just a matter of just plugging in your numbers. So I get. So let's go ahead and 6 times the square root of the top 0.3077 minus 0.3077 divided by 1/4 0.0887. Okay. It's 219. 2. 3964. Okay, now let's say for a portion of people who have Netflix, oh, 219 64. Okay. All right. So far, so good. I think it's pretty straightforward, right? It's just a matter of kind of plugging in your numbers, going from there. Okay, and I think I got this all written out here in this calculations. Great. Okay, and then I just put this slide here, and I feel like it's okay. Like, we don't have to spend too much time because I think you've seen confidence intervals enough by now to kind of know the proper interpretations. That being, if your interval goes from 29.39, 21.9%, so basically around 22% to like 40%, 39.64%, we can ask, do we have evidence that the proportion P is different from 20%? We say, okay, well, 20% is not inside my interval, it's outside of the interval. So we have evidence that it's not 20%. Do we have evidence that it's different from 25%? Well, 25% is inside the interval, so we don't have evidence that it's not 25%. But on the other hand, do we have evidence that it is 25%? And then as far as the confidence interval goes, we can never use the confidence interval to say that the proportion is exactly equal to some number. So even though 25% is a plausible value, we're not allowed to say that the proportion P is equal to 25%. Okay. I went over that very quickly, but I think that's okay, or I don't know. Let me know if you want me to slow down and go over any of these things point by point or anything like that. Oh, let me also give you your first view quiz answer for today. Today's first view quiz answer is the letter D, D as in dog. D as in dog is your first view quiz answer for today. D, D as in dog. Okay. All right, so we will move forward, and now rather than the confidence interval, we will introduce a hypothesis test that we can use for categorical variables. And so the first one that we're going to look at is the chi-squared goodness of fit test, the goodness of fit test, okay? And so this, it looks like an X, okay, but maybe a little curlier. This is the Greek letter chi, and it looks like you might pronounce it chi, but again, we pronounce it chi. All right, and the goodness of fit test is used to test how well the data fit an expected set of proportions, right? So we ask, how good is the fit between what we observed and what we expected, right? You have your expectations and the reality, and we ask, how well do those things match, right? How good is the fit between the expectation and the reality, or basically what we expected and what we observed? And so for the goodness of fit test, there's basically just going to be one categorical variable, all right? And that categorical variable could have multiple categories, right? So when we were doing the confidence interval, it was a dichotomous thing. Things are either yes or no, okay? But here we could have multiple categories, right? We could talk about like pieces of candy, right? So are M&Ms, are the colors in equally distributed? Like, do you have the same proportion of red as you get yellow and green and blue and brown? And is that it? I don't know. Okay, whatever. Right? Are they in equal proportion, or do you get like more of a certain color or something? Right? So you could say you'd list off all of the categories and you'd write down the kind of proportions, right? Or however many categories you have, right? And so when you do this, your hypothesis, it gets written as a list of categories and expected proportions. So your hypotheses will be basically the proportion or the probability of this category is this number. The proportion of this category is this number. The proportion of this category is this number, right? And basically all of those things have to add up to 1 or 100%. Okay. So here's an example. And it's a bit, I never took biology in college, and I imagine many of you have taken, like the LS series and stuff. So this is based off of my very, very rudimentary memory of like high school bio and stuff. But you have like your Punnett square, right? And you might have these whatever the phenotypes or something. I don't know. Okay. So anyway, you bring these together and you have big A, big A, big A, little a, and big A, little a, and little a, right? And so according to this model, we would expect 25% of the progeny to have big A, 50% would have big A, little a, and 25% would have little a, right? And so, in this model, only 1/4 would exhibit the recessive trait, 3/4 would show the dominant trait and things like that. But, let's say we want to kind of track this down. And so our null hypothesis, right, if it says, we're going to assume that this is true, and according to our null hypothesis, then 25% should be big A. So our null hypothesis is listed as basically a list of categories and their proportions. And so we have big A showing up at 25%, big A, little a showing up at 50%, and little a showing up at 25%, okay? The alternative hypothesis will be at least one of these proportions is wrong. And anytime you have more than 2 categories, your alternative hypothesis has to be non-directional, okay? And that's because if you have 2 categories and one category is too high, then that means the other category is too low, right? But if you have 3 categories and you say, oh yeah, one of these is wrong, maybe it's too high, we've got to adjust it to be something less, then the question, right, if this one's too high, then which one is the one that's too low? Is it that both of the other ones have to be lower, or is it one is fine and then only one has to be lower? It's not clear, right? Like where do you draw the extra, or where do you make it up from? Do you make it up from one or both or multiple of the other categories or things like that? So anytime you have more than 2 categories, so 3 or more categories, the alternative hypothesis has to be non-directional, okay? All right, and then so we go out and we collect data, all right? And let's say we get 200 observations. And the observations that we count big A, we get 45. Big A, little a, we have 106. And little a, we get 49. Okay, so let's say this is what happens in our observed counts. All right, and so the question is, how good is the fit between our observed data and the proportions that we expected? Okay. Let me go ahead and do this, right? So, okay, so I'll go ahead and write our null hypothesis. We expect big A to show up at 0.25. Alternative. Okay, and then our observed data. Okay. So the total observed count, if you add up 45, 106 plus 49, we have a total of 200, okay? And so what we'll have is we want to compare what we observed, the actual values versus the expected counts if the null hypothesis were true. Okay, so if the null hypothesis were true and we have 200 total, okay, for big A, we would expect 200 times 0.25, we would expect 50 big A, okay? And for big A, little a, if the null hypothesis were true, we would expect half of the 200 to be big A, little a, and we would expect 100. And for little a, we would expect 50. Is that okay? Does that make sense as far as what counts we would expect if the null hypothesis were true? Okay, so you basically just go through and I think that's what this slide shows. You take the number and the proportion from the null hypothesis, okay? And you multiply those things out and you get 50, 150, right? So these are the expected counts of each category if the null hypothesis were true, right? Okay, and then the last thing we're going to do is we're going to calculate our test statistic, okay? The test statistic, the chi-squared statistic, is the sum of the observed minus the expected. You take the difference between what we observed and what we expected, and we're going to square that difference. And we divide by what we expected, okay? And we add this up, add across all categories. Okay, so we have 3 categories and we're going to add it up across all categories. So that's this speech. Oh, observed minus expected, quantity squared, divided by expected. All right, so let's go ahead and do that for our values, okay? So we're going to write our chi-squared value. We're going to take what we observed, our first value. We observed 45 and we expected to get 50, okay? That's a difference of 5. We saw 5 fewer than what we believe we should have, okay? So this is for big A. And then we do the next category, big A, little a. What we saw 106. If the null hypothesis were true, we expected to see only 100. So we saw 6 too many, right? And the question is that too much or is that okay? Is that within like reasonable randomness, right? And then the last one, we saw 49. If the null hypothesis were true, we expected to see 50. And that's what we get here, okay? So we go through and we calculate these numbers. 45 minus 50. We square that number, divided by 50, 0.5. 106 minus 100 is 36. or 6 squared is 36 over 100, so we get plus 0.36. And then this is 1. 49 minus 50 is -1. -1 squared is 1. 1 over 50 is 0.02. Right? All right, so you add this up and you get your chi-squared statistic to be 0.88. I think I have that on this next slide. Okay, so we go through, we get 0.88. The observed, we compare observed versus our expected. Okay. So our chi-squared value is 0.88. Okay, and then so what we're going to do is we now go to a reference table. And the degrees of freedom is the number of categories minus 1. So here we have 3 categories, big A, little a, little a, little a. We have 3 categories. So minus 1, we have 2 degrees of freedom. Okay. And it's a little bit illustrated kind of by the idea that if we have 200 total, when we were doing the expected counts, as soon as I put in 50 here and 100 here, I didn't necessarily actually have to do 200 times 0.25 to get this last 50. I just, if I knew that the total number had to be 200, as soon as I put in the first 2 numbers, the last number was kind of locked in, right? Like, because the total has to add up to 200. So as soon as you put in 2 numbers, that third number really has no choice, no freedom to be anything other than the number that will make it add up to 50. Okay, so let me pull up the reference tables. So we go to so many reference tables. Here it is. Okay, table 9, critical values of the chi-squared reference table. Okay, so we look at 2 degrees of freedom, and the very first number is 3.22. So our number 0.88 is smaller than this, which means our tail probability, whatever it is going to be over 20%. Okay. And again, always read the heading. All right. It says, note, column headings are non-directional p-values. If the alternative is directional, which is only possible when the degrees of freedom is 1, then directional p-values are found by taking the column headings and dividing the column headings in half. So anyway, all we get right now is that our tail probability, our p-value, is over 20% because 0.88 is less than 3.22. So I'll just write my p-value, whatever it is, greater than 20%. If alpha is 5%, do not reject the null hypothesis. Okay, so I think this is, I've written this, right? 0.88 is closer to 0 than the first number in the row, 3.22. This means that the tail probability is greater than 20%. If our significance level is 5%, we choose not to reject our null hypothesis. And we would conclude that our observed data do not provide evidence that the proportions listed in the null hypothesis are wrong. Okay, so we'd say we do not have evidence to say that these proportions in the null hypothesis, that they are wrong. Okay, now it doesn't prove that these proportions are correct. It's just, you know, we have 200 observations, and if this is what we observed, there's nothing here that leads us to believe that these proportions are wrong. Okay. Any questions there? Hopefully the process feels familiar, right? It's the way we calculate this test statistic is different, but kind of the idea of you go through you write your hypotheses, you go through the process to get a test statistic, you look it up in the table, and then you make your conclusion. Hopefully that process feels comfortable by now. Okay, let's take a look at another example. This one is this comes from the textbook, directly from the textbook. but I thought it was pretty fascinating, and so I want to bring it up here. Okay, this one is a chi-squared goodness of fit test with a directional alternative. This you can only have a directional alternative if it's a dichotomous variable or something with only 1 degree of freedom. So so the question that researchers posed at the start of this at the start of the study was, can people who are close to death postpone dying until after a symbolically meaningful occasion? Like, can someone kind of prolong their life somehow, right? And so the researchers decided to study death from natural causes among elderly Chinese women. They defined that as women over the age of 75 living in California. And they chose to study the time around the Harvest Moon Festival because the date of the traditional Chinese festival changes somewhat from year to year, making it less likely that a time of year effect would be confounded with the effect that they were studying. So they didn't want it to be like, I don't know, there could be, right, like during this particular week, maybe it's, people are more at risk of dying or something, okay? And then number 2, it's a festival in which the role of the oldest woman in the family is very important. And so they wanted to kind of see if that would play a role, right? And so they said previous research had suggested that there might be a decrease in the mortality among elderly Chinese women immediately prior to the festival with a corresponding increase afterwards, okay? So they're going to, this is kind of, they're going to look at a directional alternative hypothesis, okay? And so they looked at a bunch of records and they found that over a period of several years, there were 33 deaths in the group in the week preceding the festival and 70 deaths in the week following the festival. And the question is, how strongly does this support the interpretation that perhaps people can prolong life until a symbolically meaningful event, right? So we got 33 versus 70. And the question is that significant? Okay. So if there were no, if this were not possible, right? If people can't prolong life somehow, then we would expect, the probability that somebody dies before the week or in the week before is going to be the same as the probability someone dies in the week after, right? So given the null hypothesis can be stated like this: given that an elderly Chinese woman dies within 1 week of the Harvest Moon Festival, she's equally likely to die before the festival as she is after the festival, okay? Which means the probability that someone dies before the festival would be 0.5, and the probability that someone dies after the festival is also 0.5. And then we want to see if we have evidence to support the alternative hypothesis, which means that if we know, right, within a 2-week span, right, if we've got the festival on one day and you look at the week immediately before and the week immediately after, we're going to say that given that an elderly Chinese woman dies within 1 week of the festival, she's more likely to die after than before, right? And so the probability that someone dies after will be greater than 0.5 versus the probability that they die before is less than 0.5. Okay, so this is kind of the question that we want to look at, right? Okay, so let's go ahead and try this out. So in our data, we have 33 versus 70. Okay, so all right, so we're going to say death after. And then the alternative. All right, so what we observed was before we have 33, and then after we have 70. All right, so we have a total of 103 observations. All right, so the expected counts if the null hypothesis were true, okay, well, we would expect half of 103. So we would do 103 times 0.5. We would expect 51.5, right? If the null hypothesis were true, okay? And death after, we would also expect the same number, 103 times 0.5, 51.5, right? So these are our expected counts if the null hypothesis were true. Okay, so our chi-squared statistic is the sum of the observed minus the expected. We square that difference and we divide by what we expect. Okay, so we'll look at the first category. We observed 33 people who died before the festival. If the null hypothesis were true, we would expect 51.5. And we're going to take that difference and we're going to square it. And we divide by what we expect, 51.5. And then we take the second category. What we observed is 70. If the null hypothesis were true, we would expect 51.5. We would square that. And we would divide by 51.5. Okay, so let's go ahead and do this. (33 minus 51.5 squared) divided by 51.5. And then 70 plus 51.5. Okay, I get 13.29. Okay, I guess let me see a little bit more work. This is 18.5 squared over 51.5. And then this is also going to be 18.5 squared over 51.5. Right. And that gives us 13.29. Okay. We would have 1 degree of freedom. Degrees of freedom is equal to 1. We have 2 categories minus 1. We have 1 degree of freedom, 13.29. Right. So I'm going to go to my chi-squared table. Looking at 1 degree of freedom, we're between 10.83, 13, what was our number? 13.29. We're between these two numbers, okay? So our non-directional tail probability is between 0.001 and 0.0001, okay? So from the table, non-directional tail probability (0.001) and 0.0001, okay? And it says if the alternative is directional, which is our case here, right? We will take these and we will divide by 2, okay? So our p-value is between 0.001 divided by 2 is 0.0005, and this number 0.0001 divided by 2 is 0.00005, okay? So it's a very small number, between 5 in 10,000 and 5 in 100,000, okay? So it has a very, very, very low probability of happening. Okay. If the null hypothesis were true, right? It's basically saying if you flip a coin 103 times and it's a fair coin, could you get the situation where you get 33 heads and 70 tails? It is not impossible, but it happens with a very low probability, less than 5 in 10,000 times. Okay. So it happens with a very, very low probability. So if that were to happen, you would come away with the conclusion that, you know, your coin isn't fair, that it is somehow geared to kind of favor one side over the other. And so in our case, we're not flipping coins. We're asking, is it equally likely for someone to die in the week before as it is to die in the week after? And this indicates that that no, it's not somehow, and we don't understand the mechanism behind how this works, but it sure seems that the data seems to indicate that there's a greater probability that somebody will die in the week after than in the die in the week before. Okay, I think I've got everything kind of listed out here, using the chi-squared table and things like that, right? So our p-values, half the column headings. We would reject the null hypothesis. Our data provides evidence that if an elderly Chinese woman dies within 1 week of the festival, she is more likely to die in the week after than in the week before. Okay, which I thought was an interesting conclusion. Again, statistics is powerless to explain what is happening or how it works. It's just saying, you know, the data that we've observed, it can't just be, it's very unlikely to be random coincidence. Okay. Okay, how do we feel about that? Any questions there? I feel okay. All right, then let me go ahead and give you your next view quiz answer for today. The second view quiz answer for today is the letter B. B as in bear. B. B as in bear is your second view quiz answer, B. Okay. So I'm going to move on, and now I'm going to cover the chi-squared test for independence. And this technically brings us into chapter 10. I felt like the topics are so closely related that we can cover chapters 9 and chapter 10 in one lecture, and I think we will, and the chapter 10 stuff is it's pretty short, so we might even finish early today. I shouldn't make promises that I can't keep, but that could happen. All right, so in chapter 10, we introduce the chi-squared test for independence. And so now what we're doing is we're going to look at two categorical variables, and we want to see, is there an association between the variables, or are the variables independent? Now, we already experienced something like this back when we were talking about independent probabilities, independent events, and we asked questions like, is driving a truck, driving a pickup truck, is that independent from being from California or being from Texas or something like that, right? And basically we're asking the same type of question. You've got a categorical variable, does someone drive a truck or not, versus another categorical variable, is someone from California versus Texas. And we want to know, is there an association, or are these things independent? Okay. And when we covered probabilities of independent events, or covered kind of those associated probabilities, conditional probabilities, and asked if they're independent or not, there was just a very simple rule. We said if the probability of A given B is equal to the same as the probability of A given not B, then they are independent. And if they're unequal, then they're associated. Okay. Here, we're basically asking the same thing. We're going to say kind of the same thing. If probability A given B is this equal to the probability of A given not B, then they're independent. And if they're unequal, then they are associated. But we allow for basically randomness, right? So when you take your observations and you get slightly different numbers, the question is, could it be the result of just kind of random sampling? Okay. And so I have a couple examples here, or we'll work through an example, and the rest of the notes are kind of handwritten here, and I'll just I will write them out. So the rest of today's notes will be handwritten. Okay. So let's go ahead and take a look. Okay. So again, this is the chi-square test for independence. And the central question is there an association between two categorical variables? Okay. And so the example I'll run through will be, do people with diabetes and we will define this as their A1C level is greater than 6.5. And we'll ask, do they have an increased incidence rate of having high blood pressure? Okay, and this will we'll define this as systolic being over 140. Okay, so so technically we're taking like numeric variables and we're kind of making them into categorical variables, but I think that's fine. We're going to just say, does someone have high blood pressure, yes or no? And that will just be defined as, if their systolic blood pressure is over 140. And does somebody have diabetes, yes or no? And that will be defined as if their A1C level is over 6.5. Okay. Now we have to be careful about the words we use, right? So we're going to say increased incidence rate, because we don't want to say that does diabetes cause high blood pressure, or does high blood pressure cause diabetes? We don't want to say anything like that or suggest anything like that, because that's not what the data is not capable of even suggesting something like that, right? If we're taking observational data, we can't make any kind of cause and effect conclusion or cause and effect even suggestion. All we can say is, are these kind of risk factors, do they seem to happen together, or are they kind of completely independent of each other? That's kind of what we're asking here. Okay, so one thing to note is both of these variables are dichotomous. It's either a yes or no, right? So both variables are dichotomous, either yes, they have diabetes, or no, they don't, or yes, they have high blood pressure, or no, they don't. And this allows us to kind of arrange our data in a 2x2 table. Now, we can, there are methods for variables that have more than two categories. The process is the same, it just, the work becomes more tedious, okay? We can analyze variables. Just the work becomes a little bit more tedious. Okay, so here is just some purely fictional made up data. Okay. Don't like cite these numbers. Okay, so this is a two-way table. We're going to say we got people with diabetes versus no diabetes. And we have high blood pressure. And we'll say not high. Okay. Put in columns for totals, and these are going to be the numbers I have. I've got 20 people with diabetes and high blood pressure for a total of 120 with high blood pressure. I'm going to have 20 people here, 260 here for a total of 280. That leads to a total of 400 here, total of 40, and a total of 360. Okay. So these will be our quote unquote observed data. In quotes, because I just made it up. But we're going to pretend that this is what we observed. All right, how would we write our hypotheses? Okay. So our hypotheses, basically, we don't, our null hypothesis will be that the two variables are independent. We would say that having high blood pressure is independent of having diabetes. Okay. Symbolically, we would write something like this. We would say the probability that someone has high blood pressure, given that they have diabetes, this is equal to the probability that someone has high blood pressure, given that they do not have diabetes. Okay. And basically what we're saying is that whether someone has diabetes or does not has no influence on the probability that someone has high blood pressure, that the incidence rate of high blood pressure is the same whether somebody has diabetes or not. Okay. And that would indicate that there is no connection, that they are independent. The alternative hypothesis is directional, right? So here we have increased incidence rate. So this is a directional alternative. We're going to write basically people with diabetes have an increased incidence rate of high blood pressure. Okay, or symbolically. Basically, we're going to just change this equal sign into a greater than sign. Let's say the probability that someone has high blood pressure if they have diabetes, okay, is going to be greater than the probability that someone who doesn't have diabetes has high blood pressure. All right, so let me just pause here and just make sure that we feel comfortable with the way I've set up the hypotheses. Okay. Could I switch them? Yes. So you could switch them, and if we wanted to, it is also okay. Would be probability of diabetes given high blood pressure, probability of diabetes given not high blood pressure. Okay, it doesn't quite align with the exact same question. Do people with diabetes have an increased incidence rate of having high blood pressure? This would be a little bit more like, do people with high blood pressure have an increased incidence rate of having diabetes? But the answer is, if you reject this null hypothesis, then you will certainly reject this null hypothesis as well. What does the line in between high blood pressure and no diabetes mean? So this is, again, this is from conditional probability. The vertical line means given, right? So probability of A, B is equal to the probability of A given B, right? So this is, you might have to review your chapter 3 notes, I think from week 1 Wednesday. I think I know it's been a few weeks. I mean, it feels like a long time ago, but then again, it was also only 3 weeks ago. So I know, like, the things, the summer classes just go quick, right? That's the pacing of a summer class is fast. Hopefully not too terrible, but anyway. Okay, is that all right? So the vertical line means given, and it's the probability of A given B. And you know, we had questions about that. Okay. All right, so let's take a look, and we want to ask, you know, if the null hypothesis were true, what counts would we expect? Okay, so what we're going to do is we're going to copy the row and column totals from the observed table, from the table of observed counts. Okay, so I've got diabetes, no diabetes, high blood pressure, and not high. I'm going to just abbreviate blood pressure. Okay, and our totals, we had 120, 280, 400. And we had a total of 40, 360, and 400. Okay. All right, and so the question, what number should we put in here? Okay. the expected count if the null hypothesis were true. Okay. So what we can say is, well, let's look at this, right? So we'll say the expected count of people with diabetes and high blood pressure. All right, so we can just say, all right, we'll take our grand total and multiply by the probability of diabetes and high blood pressure. Okay. And remember, the null hypothesis basically states that these two things are independent. So if A and B are independent, do you guys remember what the rule is? And the probability of A and B is equal to the probability of what? A times the probability of B, right? It's just becomes the product of the events. If you have events that are independent, the probability of the two things happening together is just the product of the two events. So that's where, again, you might have to look back at your chapter 3 notes, but hopefully this feels a little bit familiar, right? So if A and B are independent, this is what's going to happen. Okay. Why do we because we wanted to get the expected counts, right? So the probability of diabetes and high blood pressure is this. And so let's say it's like 3% or something, right? Then how many would we expect? We would take how many we have total, right? 400 people times, maybe the combined probability of 3% to get whatever number should go in here. Okay. So this part, we'll leave in the grand total for how many people we expect, multiply by, we're going to use the independent rule. And we're going to say, okay, well, this is going to be the probability of diabetes times the probability of high blood pressure. Okay. And so our estimated probabilities for these things, we can just kind of use from our table here. All right. So the probability that somebody has diabetes will be basically this column total, 40 over 400. Okay. So this will be the column total divided by the grand total, which is basically 40 divided by 400. Okay. And then what's the probability that someone has high blood pressure? We're going to do 120 out of 400. Okay. Which is basically my row total divided by the grand total. Okay. And we're going to multiply that by the grand total. So basically what we're saying is, if you look at, the diabetes, we have 40 out of 400. So basically like 10%. And probability that someone has high blood pressure, we have 120 out of 400, basically like 30%. Okay. So this basically becomes 400 times 0.1 times 0.3. And we have 400 times 0.03, or we have 12. Okay. So there's a question in the chat. It says, is this the rule that column total divided by grand total would be the give us probability of diabetes. It's just kind of an estimated probability, right? Based on the data, what's the relative, what proportion of people have diabetes, right? If we just ask, so again, if you think back to chapter 3, right? So if you think back to chapter 3, if I just asked, what is probability of diabetes? Okay, you just kind of take total number of people with diabetes divided by total number of people. And you would say, okay, well, we have 40 people total diabetes, 400 people total. You get something like 0.1, right? So I know it's been a long time since we looked at this probability stuff, right? And then again, if we ask, what's the probability that someone has high blood pressure? We would just do, the total number 120 divided by 400, and we would get 0.3. And then, so if they're independent, what's the probability of diabetes and high blood pressure? We could multiply these things together if they're independent. Which is what we're saying. If the null hypothesis are true, what counts would we expect? Okay. Diabetes times the probability of high blood pressure. And we would get 0.1 times 0.3. This would end up being 0.03. Okay. And so if this were true, the number we would put in here would be 12. Okay. So if the null hypothesis were true, out of 400 people, we expect 12 to have diabetes and high blood pressure. Okay. Let's chime in. All right. Is that okay? How I got this number 12 right here? Okay. So let me go to our next slide. All right. So let me just kind of again, oops. Make our tables here. And we're going to have two tables side by side this time. Okay, so our observed, and I'm just going to abbreviate, diabetes, no diabetes, high blood pressure, not high blood pressure, 20, 100, 120, 20, 260, 280, 40, 360, 400. Okay. And here, 40, 360, 400, 120, 280. This is the expected. Hypotheses were true. High blood pressure, not high blood pressure. Diabetes, no diabetes. Okay. And then we'll put in our first number here, which is 12. Okay. And we could go through the process and we could say, okay, what proportion should go here and what number should go here and what number should go here. But we actually don't even need to do that. Sorry, before I keep going, we have a question in the chat. It says, could we also use the probability of A given B equals probability of A and B divided by probability of B for calculating the expected value? Yes, you could use that. Okay. You could use that. So the question here is, in order to get this 12, could we have done something different? Yeah, there's lots of options you could have done, right? So another way you could have done this, and perhaps this, for this example, it might have even been easier. You could have said, well, okay, we have 120 people with high blood pressure, right? And we could have said, so this is just an alternate, right? We could have said the probability that someone has diabetes is just 40 out of 400, right? So probability of, say, diabetes, 40 out of 400 is 0.1, okay? So therefore, the kind of the expected count, we would expect 10% of 120 to have high blood pressure and diabetes, right? We would just take 10%, right? If this proportion 40 out of 400 holds, then it's got to be 12 out of 120, right? Which also means it's got to be 28 out of 280. Okay, we could have also done that. So there's lots of ways we could have done this. Okay, so yes, but I do want to just point out that once this number filled in with 12, this number, there's no choice. Okay, we could go through the process and we can say, okay, well, what's 10% of 280? Okay, well, that's 28. Okay, but really we don't even have to do that. We have to just say, well, 12 plus some number has to add up to 40. Okay, the only number that you can add to 12 to get 40 is going to be 28, right? 12 plus some number has to be 120. It has to be 108, right? 28 plus some number has to be 280. Well, that's a little bit harder, but it's going to be 252. Okay, there's no choice, right? So once we entered 12 into this top left corner, basically the other three numbers were kind of locked in. Okay, once we put in that first number, the other three numbers had to be locked in because of the column and row totals, right? Row and column totals. All right, and this gives us a sense. The degrees of freedom for a 2x2 table is 1. Okay, when you have a 2x2 table, which is what we have here, okay, you only have 1 degree of freedom. Okay, and it's kind of, we kind of see that once you put in one number, there's no more freedom left as far as what values these cells can take. Okay, they have to be 108, 28, and 252. There's no other choice. Okay, and if you have a larger table, for any table with R rows and K columns, the degrees of freedom is equal to rows minus 1 times number of columns minus 1. Okay. Now, why we use K for columns instead of C, I'm not 100% sure, but that's what appears in the literature. Yeah, the total rows don't count as being part of the columns, number of columns or the number of rows, right? So number of rows or columns don't include the totals. Total row or column. Okay, let's go ahead and calculate our chi-squared statistic. Our chi-squared statistic is found the same way. We take our observed count minus our expected count divided by expected, and then you add it up for all 4 internal cells. Okay, yeah, don't do the total rows, total row or total column. Just the four inner cells. And do that, okay? And then make sure you do all four cells. A common mistake, students will just do like the first one or maybe the first two, but they don't do all four. And you're going to get the wrong number, right? The chi-squared statistic, yes, you have to add this up for all four cells. Otherwise, you're going to get the wrong number. Okay, so let's go ahead and do this. We will take our observed count. We observed 20. We expected 12 if the null hypothesis were true. So we take that difference and then we square it and we divide by what we expected, which was 12. Okay. The order doesn't matter. You just have to do all four of them. So we'll just go to the next cell. We observed 100. If the null hypothesis were true, we would expect 108. We'll take that difference, we'll square it, and we'll divide by what we expected, 108. Next cell, we observed 20. We expected 28. We'll take that difference, square it, divide by what we expected, 28. Last one, we observed 260. And if the null hypothesis were true, we would have seen 252. We got this, okay? And so the question is, is what we observed, is that different enough from what we expected, or is it okay, right? We would, if the null hypothesis were true, we would have expected 12 and 28. We got 20 and 20. Is that a problem? Could this just be the result of random chance? Okay. So we get 64 over 12, 64 over 108, 64 over 28, 64 over 252. Whenever you have only one degree of freedom, the numerators all end up being the same, but the denominators will be different. So make sure you do this correctly. Okay, I get 8.466. One degree of freedom. So that is my chi-squared test statistic. All right. Does that feel okay? Getting my chi-squared test statistic, 8.466. Okay, so we'll go to the chi-squared table. 1 degree of freedom. Our test statistic is 8.466. We look that up and it ends up being between 0.01 and 0.001. Okay. All right, so let me go ahead. I'll just write this down. My chi-squared statistic is 8.466. 1 degree of freedom, okay. And 8.466 is between 6.63 and 10.83. Okay, so the non-directional probability is between 0.01 and 0.001, right? So those are my column headings, 0.01 and 0.001, okay? And again, we read the note at the top of the table because it's different for this table than it is for the T table and things like that, right? It says column headings are for non-directional p-values. If the alternative is directional, which is only possible when the degrees of freedom is 1, which is our case, the directional p-values are found by dividing the column headings in half. okay? So our tail non-directional probability is between 0, 1 and 0.001, okay? Our alternative is directional though. You know, we said the probability of having high blood pressure given diabetes, right, this is our alternative hypothesis, is greater for people with diabetes having high blood than it is for having high blood pressure for people with no diabetes. Okay, and when we checked our data, indeed, we observed 20 versus what we expected is 12, right? And so that indeed our data aligns, okay? So the p-value is half of our column headings. So we're going to say our p-value is between 1/2 of 1%, 0.005, and 1/2 of 1,000, 0.0005, okay? So very, very low probability. So if alpha were 5% or even 1%, we reject the null hypothesis, okay? And we would say our data provide evidence that people with diabetes do have a higher incidence rate of having high blood pressure, okay? Our data does provide evidence. High incidence rate. High blood pressure. Then the people who do not have diabetes. Okay, and again, we're not making cause and effect conclusions. We're only just saying that there is an increased incidence rate that these conditions do, or risk factors do seem to have a higher kind of incidence rate with each other than not. But again, we're not saying that high blood pressure causes diabetes or diabetes causes high blood pressure or anything like that. We're just saying that we're observing these two things, you know, a little bit more commonly together than not. Okay, than what we would expect if the conditions were completely independent. But it's you would need somebody who understands kind of pathology and things like that to kind of give more insight as to, you know, what's happening. Okay, and that's pretty much it for chapter 10. You have the chi-squared test for independence. There's a little bit of sections in your reading, but you know, as far as what I want to cover in our class, just kind of this one test. And you know, the textbook covers the R by K, where you have more than 2 categories per variable, but it's the same process. So if you had a categorical variable with 3 categories and another categorical variable with 3 categories, say, you know, low, medium, high for, right? So, you know, blood pressure, you could say there's normal blood pressure, high blood pressure, and like really high blood pressure, right? There's like hypertension 1 and hypertension 2. So you could have multiple categories there. And you could take another, another variable that perhaps has more things like that. It becomes the same process, except instead of a 2x2, you now have a 3x3, and now you have 9 cells. You have 9 expected values to calculate, and you have to do observed minus expected over expected, observed minus expected squared divided by expected, but you have to now do it for all 9 cells. And it just becomes tedious. It's the same process, just more tedious and more potential for making a calculator mistake. So as far as this class goes, and as far as quizzes and the final exam, you will see at most a 2x2 table. Okay, I will not put anything bigger than that, just because I feel like it's reasonable to expect you to have to calculate 4 cells and then just make sure you do those 4 cells correctly. But if you do 3x3, it just grows really fast and becomes 9 cells, and then it's like you accidentally key in the wrong thing and then everything blows up. So our class just 2x2, but it's the same process. It's the same process. Oh, you know what? I guess before I let you go, I will just demonstrate. We spent this whole time, and I do feel like a tiny bit like, oh man, the truth is, we do things with our calculator very frequently, and it makes everything so much easier. Oh, last view quiz answer. Thank you for that reminder. Last view quiz answer is the letter A as an apple. A as an apple is the last view quiz answer. Okay, let me just show you real quick how we would do something like this in R. Okay, so I'm going to just create a vector counts, or not a vector, it's going to be a matrix. And the matrix, we have 4 cells. So I'm going to put in 20, 20, 100, 260. And the number of rows is equal to 2. Okay, so here's my counts. This is basically the observed counts that I have. And then just type in chi-squared test. And I do x equals counts. I think, is that it? Oh, I have to do, in order to get it to line up exactly with our answer, I have to turn off the correction, the continuity correction, which I will not bother explaining here. And let me make this a tiny bit bigger. But basically, I enter counts, and then I do chi-squared test x equals counts, and there you go. You get x. The chi-squared value is 8.46, which we found right here, 8.466 or 8.4656. Degrees of freedom equals 1. And we said our chi-squared values between 1% and 0.001, or the non-directional probabilities between 0.01 and 0.001. And here the p-value is this. I would have to, is there, I guess I had it. Is there a thing for the alternative, directional alternative? Maybe not. Okay. Well, anyway, it does it real quick for you, right? We went through a bunch of work. Okay. Oh yes, sorry, to repeat myself, the last view quiz answer is A. A as an apple is the last view quiz answer. Okay. Could you have a non-directional test with degrees of freedom equal 1? Yes, you could have a non-directional test, right? We could just say, is there a difference, right? Is there a difference in the incidence rate of high blood pressure? And you would have a non-directional test and you'd leave it as is. Here we just wanted to say, is diabetes a risk factor for having high blood pressure? Meaning, do people have a higher incidence rate? And so that makes it directional. But you could have non-directional tests just as easily. Okay, that's it. That's it for today's lecture. So we will end here. And have a good evening, have a good weekend, and as always, your homework's due. and you have a quiz on due on Sunday. It'll be released on Saturday. Make sure you take your quiz. Okay, we'll see you guys on Monday. Have a good night. Have a good weekend.
Thank you. Have a good weekend.
Thank you.